We're 2 minutes into class, so let's actually get started with class. So let me find the warm up and open it up. So we want strobe. It's going to look remarkably like the first class. I mean, it is different, but it just looks really similar. So I'm going to share my screen with that. And let me switch this to there. Now you've got the strobe on. This says, in each case, a sphere is moving from left to right next to a tape marked in meters. A strobe flash photograph is taken every second, and the location of the spheres is recorded. The total time intervals shown are not the same for all the spheres. Rank the magnitude of the displacement over the first 3 seconds. So in the first class, this was on Thursday of last week, we looked at the biggest displacement over the first 2 seconds. Now we're looking over the first 3 segments. Take 20 seconds, find the most displacement to the least, rank them in your head. I'll give you 10 or 15 more seconds and we'll talk about it. Okay, that seems like it's enough time. So I want plenty of audience interaction, so feel free to unmute yourself, hit the space bar, whatever you need to do, and tell me what had the least displacement in the first 3 seconds, the least.
B.
B. What had the most?
D.
D. So definitely D had the most at 9 meters in the first 3 seconds, followed by, looks like C with 6 meters. A was third place with 4 meters, and then B, like Bravo or Boy, had 1 meter in the first 3 seconds. So we're just making some comparisons that should have been pretty straightforward from last class. And if we were not in last class or just too much asleep, hopefully that woke us up. If you have late arrival, then welcome to school. If you had a first period, hopefully it won't be as exciting as this one's going to be. I'll try. Okay, so let's see what we have. So the walking lab, you were supposed to submit your walking lab by the end of day on Thursday of last week. Your walking lab should have looked something like this. I'm going to open mine up and let's talk about it. Let me share it. There we go. And if I scroll up, there are my graphs, as beautiful as they can be. On the left side of my screen, I did rewrite out that y equals mx plus b and derived our formula where we've got x as our position is equal to velocity times time plus the initial starting position. So our position can be calculated by displacement plus the initial starting position. Let's see if you can see. Yeah, you can see my cursor. So let me let them in. So we can see that we can determine where we are based on how much we were displaced from our initial position. This is the formula we want to use throughout this work. Hopefully you did. I hope you didn't bring yourself back to y equals mx plus b, but that's okay. You turning in the work last week was about accountability, keeping you on track, not about grading you on something you could have gotten the answers from the other 500 people taking this class. So let's take a look at it. When you drew your graph, make sure you always put a title. That's absolutely always a necessity. You've got labels for your X and Y axis and units. So I have position X in meters, I have time in seconds, and I call this position versus time graph. I graphed all 4 walkers, 1, 2, 3, 4. I labeled the 1, 2, 3, 4 on the lines. Apparently I forgot to label number 4, but I put over here what they were: slow, fast, back, and down. You can also see that on each line, I drew a circle. So that way, this is where I got the coordinates for the slope. My rise over run, change of y over change in x. And I wanted to do that from as far away as I could. I looked for an area like this where it kind of crosses through a T of the graphing paper. But if I couldn't find that, I tried to do it where it crossed right in the middle of a line so I can more accurately describe or figure out where I am in the graph. I do want to make sure that they're plenty separated. So if I do them really close together, any error is going to be multiplied across the line. If I do them on opposite ends, any error is then divided along the line, which makes my error look smaller. Okay. I also wanted to make sure that my graph is nice and spread out. So if my longest time is like, I think it was 13, looks like there was a 13 point something seconds. I did my line out to 15, And then we went out to 10 meters, so I let it go up to 11. So I want to make sure my information is spread out in the graph and not just tucked into a tight little corner. So your graph should look something like this. I did this at home, I think Friday afternoon, so Thursday or Friday afternoon. So I could have made an error, but no one in first period was willing to speak up. So if I did something wrong, you should tell me so I don't embarrass myself in fourth period. So graph should look like this. This is what we should have. As we come up to our calculations here, we had to come up with a formula for the line. We did not want to use y equals mx plus b. We started with that formula just so we could derive a physics formula. Start from an area that is familiar and then make adjustments. So 1, 2, and 3 lines all started at the origin. Mr. Hennessy's walking started at the origin at time point 0. So I graphed it from there, y-intercept is 0. Then I had to calculate the slope. We can see that the slope is my velocity from up here. I got a slope of 0.72. So then x equals 0.72 time plus 0. So I dropped the 0. So I can calculate any position if I'm given the time. Now that I know that, I want to look back at the graph and ask some questions. Independent and dependent variables. Every graph has an independent and dependent variable. What is the dependent variable for this graph? Unmute and talk to me.
Position.
Position, why?
It's on the y-axis.
Okay. Why would time not be the dependent variable?
You can't really change time.
Right, exactly. So time is always going to be on the x-axis. It's always going to be your independent variable. Time doesn't care about anybody. We could sit here and do whatever we want. Time just keeps clicking by. It's not dependent on anything. But the displacement that Mr. Hennessy experienced while he was walking was very much tied to time. It was dependent on the time being independent. If he had more time, he could have gone further, right? If we took away some time, he couldn't have gone as far. So time is our independent variable, and it's always on the x-axis. And then whatever we graph on the y-axis is our independent variable. And I like to explain it that way because some people do get locked into, if it's here, it's independent. If it's here, it's dependent. That's the way it is. And it's like, well, let me think about it. Why would position not be independent? It's like, well, because position is going to be velocity times time, and it depends on how much time you have. Makes sense. Let's go back to the calculations. So if your slopes are somewhat close to mine, that's great. They don't have to be exactly the same as long as they're in the same neighborhood. If they're really crazy different, I would want to look at what points along the line you chose. So for my fast, I got x equals 2.43 t plus 0, so I didn't include that because the y-intercept is being 0. You can see where my coordinates came from, my change in y over my change in x, change in y over change in x. I try to spell it out as best I could. So for all of that, I come to number 3. In this one, I got a slope of 1. So x equals t. 1 second equals 1 meter. 5 meters, 5 seconds. For the down line, I don't know the y-intercept. So I have to come up here and I can see that the line continues up. And this looks like it should be, well, if this is 11, this is 12, and this line would kind of come through here. It'd be 12, nearly 13. I can see that, but I need to calculate what it's going to be. So how did I do that? I'm a little ashamed that I put B there. I should have put X naught, but it was a long day. So I was able to calculate my slope, and I got negative 1.25. So X equals negative 1.25 times T plus, should have been X naught, but it was a long day, so I put B. Then I picked any point on the line. I happen to pick one of the points I used to calculate the slope. That doesn't matter. As long as it's a point that's on the line, I entered in the position and the time. That allowed me to solve for my y-intercept. Then I go back to my formula. X equals slope times time plus initial position. So that allowed me to get the formula for that fourth line. Does it make sense so far? Everybody okay? We can nod. I can see like 3 people on the screen there. At least those people are nodding, so we're good there. All right, awesome. So let's look at the questions. I'm going to pull the worksheet over, and then we can look at the questions and finish this guy up. So what were those stinking questions? What does the xt graph, or position versus time graph, of constant velocity look like? Well, if we know the slope is velocity. And if the velocity is constant, the slope would be constant, meaning unchanging. So it's not going to be a parabola. It's going to be a flat line. Whether it's flat horizontal or flat at some angle, it's a flat line. So that's what I've got for number 1 there at the bottom left corner, flat line with a single slope, i.e. linear. Make sense? Sweet. What quantity corresponds to the slope of the graph? We just said that, so that's kind of a freebie. The slope of this particular graph is the velocity. What quantity corresponds to the y-intercept of the graph? Well, for 3 of the lines, it was the initial position. It's the origin, but it was the starting point for 3 of the lines. So I put starting position x naught at time equals 0. How can you tell just by looking at the graph which person walked the fastest? Somebody else answer that for me. How can you tell just by looking at the graph, not doing any calculations, who was walking the fastest?
Usually the one with the steeper slope.
All right, let's see what steepest slope, number 4, that's what I wrote too. Differ is someone started at x equals 40 meters and walked towards x equals 0 meters. What did we get for number 5? I know there's not a lot of us in this class, but you still got to talk.
The slope be negative.
The slope would be negative, just like with the last one. Slope is negative slope, i.e. the down line. All right, so that gets us through there. Did you have anything different that you wanted to discuss? Any confusion on this particular assignment? You don't have to do that. I was doing that so that I could show you and make it part of a discussion. It makes it easier for me because if I get something wrong, when I do this and then you guys say, hey, we all got something different and all of our answers are the same, it's different than yours, I want to be able to go back to mine and say, okay, well, this is where I pulled mine from. Where did you pull yours from? So for me, it's helpful. For you, no, it's not required.
Okay.
Absolutely not required. Not is just saying that's my starting position. Anything with the subscripts 0, so not like x naught means initial position. In the first 3 lines, the initial positions had to be 0. But it's a good question because when we get into kinematics, we're going to have v naught, our initial velocity.
All right, thank you.
Everybody else good? So let's stop sharing on this one and let's see what's next in our agenda. Okay, I want to talk a little bit more about this, just taking what we have and give an example. So let me share from this other screen. My Canvas, so let's share application, Chrome, share. Okay, so if I draw a quick graph, and I've got this axis, and then I say this is x in meters, and this is time in seconds. This has a title. I feel like I have to put it on there because I just demanded that you do it. All right, and then I draw a shape and I draw a line. That's what we just had, right? With the walking lab, we had a position versus time graph. And we said the slope was what again? Tell me what the slope of this line is. What does it represent? Graph velocity. We would want to draw another, I'll draw another graph. So I need shapes. I can draw this line. I can draw it there. Or even better, because velocity could be negative, I could take that line out and I could put the line in right here. And then I can say that this is velocity in meters per second. And this is time in seconds. Okay, and then how would I graph velocity then? What would it look like? Okay, would it be positive or negative? And say, I don't know what the value is because there's no scale there. But I can see that that's a positive line, so it's going to have some positive value. It only has one value because there's only one slope there. So I could graph then, let me change the color, let's see. What if we do black? So what if we do this? Couldn't we say that that is the velocity then? And then I could even go so far as I can put a little arrow end on it and just say that's the velocity then. I've just graphed the velocity. So if I have to have velocity in order to change my position, right? Because if I have no velocity, I'm not moving. So I've got no displacement. looking at my velocity graph, is it changing or is it constant?
Constant.
It is constant. So if I were to change, if it had a change, what would that be called? In order to change your velocity, what do you have to have?
Okay, I might have cheated from the homework, but is it acceleration?
It is totally acceleration, and it's completely okay to cheat and look ahead. No penalty for that because it helps with the interaction. So this graph, does it have any acceleration?
No.
No, because the slope of this velocity graph is what? Because the slope of, we get acceleration from the velocity graph. So let me go, the slope of this gives me this. The slope of this gives me acceleration. Okay? So we get acceleration based on the slope of the velocity graph. We had a constant velocity. There was no acceleration. Okay? Now, if we had a change in velocity, we would get an acceleration. But that's what I wanted to show you is we've talked about position graphs and we've talked about how the slope of the position graph gives us velocity. But I also wanted to let you know that you can graph velocity and the slope of that velocity graph will get you acceleration. Okay, so now we can get out of that. Stop share. And let's see where we are. Okay, now we're at the point where we talked about the graphs, independent, dependent variable, talked about, okay. What about homework? So graphs 1, 2, 3, and kinematics graphs. Now they're listed as being due 1 week from today. Right now we have a quiz 1 week from today, and I would hate for you to roll in on quiz day and have a ton of questions about the homework. So I'm gonna ask that you, in your mind, rewrite the due date of the homework to be Wednesday. That way, if you roll in on Wednesday, if you've tried every problem, you can bring forth every question possible that you would have. We can shore up all your knowledge on Wednesday. When you come in on Monday, last minute questions for a couple minutes, then I'll turn the class over to you and let you take the quiz, I hope. If we change the format, I'll let you know on Wednesday. But right now, I want you to get the homework done by then. For those of you, actually let me rephrase. I'm gonna have an expectation that everybody started the homework, and I want to open up the discussion to any questions, problems, concerns, or misunderstandings of the homework. Let's talk about and fix those now before we move forward. Any questions on the homework? The graphs determine the horizontal position X of the cart at 9 seconds if the cart is located at 2 meters at time point 0. Okay, so we know from our formula that position is equal to displacement plus initial position, right? X equals VT plus X naught. Well, it's given us an X naught here of 2 meters, right? So can we determine in the first 9 seconds how much displacement it had? So
yes,
how?
because it was within the first 2 seconds. I don't know.
How did you do it though? I'm asking not to quiz you, but because there's like 15 other people staring at you and probably half of them haven't even looked at this worksheet. And I want you to teach them, looking at the graph, how can you determine in the first 9 seconds, how can you determine the displacement using this velocity versus time graph?
Because it starts at 0.8 and then after the first 2 seconds, it goes to 0.4. So the displacement is now less than it was.
Okay. You mind if I take over for a second?
No, take over.
Okay, that's perfectly fine. Thank you for being willing to talk too, because the interaction is going to make a world of difference for your classmates. The classes that do better on the test are the ones that can feel comfortable, talk out, and learn from each other, okay? This is a velocity versus time graph. So what I say now only applies to velocity versus time graph. When you're looking at the graph, if I were to shade in the area under the curve, and which means is take your pencil out, take your worksheet out if you printed it, or if you drew it yourself, if you shade in the area between the graph, the line that was drawn, and the axis, the x-axis. you end up with what looks like a crooked bow tie, okay? And if I take this out, I'm gonna try to show it on the screen. Can you see my shaded area? It's like I shaded in here and here. All right, so if you can see that, I've shaded in the area under the curve for the first 9 seconds, okay? That gave me 2 triangles, didn't it? Y'all can nod, yeah. I got 2 triangles. The triangle above the curve, above the x-axis, and then the triangle below the x-axis. So what I end up with is I've got a displacement based on that. Now the area above the axis is positive. The area below the axis is negative. If I were to sum those 2 values together, that would be my displacement that I experienced in the first 9 seconds. Now, we know that displacement is velocity times time. This is a velocity graph. It's velocity versus time. So if we want to multiply the 2 things that we're graphing, velocity and time, we look at the area under the curve. If the math tells us that we want to divide those 2 things, velocity divided by time, we would look at the slope, right? Rise over run, velocity over time. So if you're wanting to divide to get your answer, you look at the slope. If you're wanting to multiply, like, man, I really need displacement. Well, how do you calculate displacement? Well, it's velocity times time. Okay, if you want to multiply, then you need to do the area under the curve. So in order to solve this, I would say, well, if I shade the top area, the top section, which it gives me the first 4 seconds, I'm above the x-axis, I calculated that as 1.6. Then the second segment from 4 seconds to 9 seconds, I got negative 2.5. So then I put that all together and I said, well, my starting point was 2. I added 1.6, but then I subtracted 2.5, and that gave me a total displacement. Now, it's okay if this is confusing, and if I had access to my dry erase board so you can see the whole thing, I'd really start talking, but think of it like this. The graph starts out positive, right? A positive velocity means I'm walking forward, okay? I'm moving in a positive direction, but the velocity is starting at 0.8 and it's slowly becoming 0. That means I'm walking fast and I'm slowing to a stop. Then the velocity at 4 seconds starts to go negative. That means I'm starting to back up. And I'm backing up faster and faster and faster because at 9 seconds, I'm going -1 meters per second, meaning I'm backing up at 1 meter per second. I'm going faster backwards than I was forwards. Okay, so this is not a position graph. You cannot think of it that way. You've got to say, well, in the beginning on this graph, I have a positive velocity. That means I'm moving forward. Well, at 1 second, I have a smaller positive velocity. Oh, I must have slowed down. At 3 seconds, an even smaller positive velocity. I must be going even slower. And then when that velocity hits 0, that means I came to a stop. And then it went to negative. That means I started going backwards. And that's why that area under the curve is negative, because I'm starting to head back towards the origin. These take practice. And I'm glad we're having this discussion because these do take practice. At first, this is the kind of thing you want to push away from. You go get coffee, come back and wait till I'm done talking about it and hope it just goes away. It doesn't go away. Okay, so definitely practice on these. If you get stuck on it when you're working on it, let's talk. Send me an email. Let's set up a time to talk. Come to tutorials. We'll have those going really soon. I know we don't do them on Monday mornings, but we should have them going this week. So make sure we're communicating. How are we doing on that question or any other question?
So for the answer to that question, would you just add the 2 triangle areas?
You add them, knowing that one is positive and one is negative, you add those together, and then you also add in your initial 2 meter, because you started at 2 meters. So you take that displacement from 0 to 9 seconds, which is your 2 triangles, yes. But no, it's kind of like, you ever race a younger brother, sister, or cousin, and you let them have a head start?
Yeah.
So they're starting out 2 meters ahead, plus they had a displacement over 9 seconds, and all of that adds up to their total displacement.
Thank you.
I would say X equals 1.1 meters. But usually in my math, I don't keep up with the units until the very end, just because it becomes over. The formulas sometimes become overwhelming, and I want to just save my sanity. And at the very end, I just come back and say, well, I was measuring displacement, so I know it's meters. It's probably not the best habit, but I'll just be honest with you. It's my habit. Anything else on the homework? Graphs 1, 2, 3, kinematics graphs? Today in class.
Okay.
So I'll pause on that question because we're going to do that. Let's see. That's actually the very next thing we do. We're going to do that together as a part of today's activity. So I know, like, when you get to those and you're looking at that and you're like, I don't even know what to do with this. You should see the on-level classes when they see this for the first time. It's like heads exploding. But you guys are going to see it. You're going to realize how easy it is, and it's going to be no big deal. All right, so since that question kind of leads us into the next thing, let's go ahead and jump over to that. You can follow along in Canvas. Follow with my screen too, but in Canvas, I'm going to be pulling up 2 different worksheets. Each one has 4 problems. I'm going to do number 1 from each of them, and then you're going to finish those and then do an analysis page that's due today. So if we get moving, you should have close enough time to get it all done. So let me pull it up. It's, let's see, what is this called? Need to share my application. Share. All right, so position versus time graph. This is the storybook problems. So story problems listed under week 1, today's date in Canvas. We've got the storybook problems. There's 4 storybooks. Basically, it gives us a story. We're going to plot this position versus time. Now, I've already went ahead and took the time to put the axis on here because it's really miserable to sit here and watch me write the little numbers in the whole time. What we do want to do is make sure that we list the correct ones. So when we're doing this, we can read through the story. And it says, Albert lives 1,000 meters from school. So I'm going to scroll this, let's see, 1,000 meters. So I know that's at least one distance I'm going to need. And if he walks in a straight line from his driveway to the front entrance, it's 1,000 meters. Today, he walks the first 500 meters in 5 minutes. So I know there's 5 minutes. And then he stops to talk to a friend for a minute. So there's a minute of him not doing anything. So let me write down that minute. And then what happens? He and his friend walk at a slower pace, covering the final 500 meters in 9 minutes. So that's a total of 15 minutes and a total of 1,000 meters. So when I set my scale on the graph, I need to make sure it covers 1,000 meters and covers at least 15 minutes. Now, in this case, I did stretch it out fully. If you cover at least 3/4 of your graph, that's important. Don't try to shrink everything into just this little box and like, oh, I just want to graph it all here. So there's the graph. That doesn't work. That would not be acceptable. So we've got this. So now we need to graph his position versus time. So it told us, let me use this shape and that color. It told us that he covered 500 meters in 5 minutes. So 500 meters is here, 5 minutes. So it's going to go to that point right there. So his first segment, that's his position versus time, right? He went 500 meters in 5 minutes. Now next, it said that he stopped and talked to a friend for a minute. So what does that line look like?
It would be a flat line because he wasn't moving.
Okay, does that flat line go back down to 0, or where does that flat line start at?
It just goes across from 500 meters.
Exactly. So he's still at 500 meters from home, but he stood still for 1 minute talking to a friend. So there's my 1 minute. Then they walk together at the same velocity because they're walking next to each other. So I don't have to draw 2 different lines for the 2 different people if they're together. And they went another 500 meters in 9 minutes, which would take us to the 15-minute mark in a total of 1,000 meters. Because we can say that school is way up here. That was not good. Let's see. School is right here at the 1,000-meter mark. where home is at the origin. So he is now 1,000 meters from school, and it took him 1,000 meters from home at school, and it took him 15 meters to get there. From what we've done so far, does this make sense to you guys? Are we okay with this? Okay. All right, now, there's 4 problems on this worksheet. I've done number 1. You guys are going to do number 2, 3, and 4. But before you take off and do that, let's look at that second worksheet, because that is graphing velocity versus time. Again, I've already set up the axis so that you didn't have to sit through the misery. But when you go from position versus time to velocity versus time, the x-axis is going to be scaled and set up identically because it's the same time scale, right? The y-axis will change because instead of being displacement, it's going to be velocity. So we need the first one. We're going to come back here and we're going to say, okay, we need to know the slope of line 1, line 2, and line 3. So the slope of line 1 is going to be based on rise over run, correct? So we're going to have 500 minus 0 over 5 minus 0, which equals 100 meters per second, right? We okay with that? I'm just basically looking at this point and this point. For line 2, that has a 0 slope because it didn't rise at all. So we know that the slope here is 0 meters per second. And then for segment 3, we're starting at 500 and we're going up to 1,000. So we have 1,000 minus 500. That's my rise. My run, I'm starting at 6 seconds and going to 15 seconds. So 15 minus 6. That's going to be the same as 500 over 9. And when I calculate that, I got to pull a calculator out because I'm not that good in math. 500 divided by 9. I get 55.5, so I'm going to round that up to 56. Okay, so now I've got the slope of each of those lines, right? We should be okay with how I got the slope. I looked at 2 points along the line, and I did the change in y over the change in x. And that's the slope for each line segment. I'm going to graph those slopes now because the slopes are the velocities. So the very first line segment goes for 5 seconds, and it's at 100. So I'm going to come over here. It's at 100, and it goes for 5 seconds. The next one is 0, right? And it goes for, not seconds, minutes, sorry. It's 0, and it goes for 1 minute. So I need to come back down here and draw it. Actually, it's drawn from first period, still sitting there. So I've got this 1 minute at 0, and I can connect those 2 graphs. So Albert goes from 100 meters per minute to 0 meters per minute. This is while he's standing still. Then what happened? From 6 minutes to 15 minutes, he moved at 56 meters per second. So we come back over here. We go to 56, which would be right around here, I think. And he does it from 6 minutes all the way to 15 minutes. And we can connect the lines. So this is your velocity versus time graph. So when I was asked about graph number 2 in the homework, how do you graph velocity versus time? When you've already graphed the position versus time, you get the velocities, record them, write them down, whatever. Then you just simply graph that value over the same length of time. He went 100 meters per second for 5 seconds. Then he stopped, right? Then he started back up, but he was moving slower. This is how you do it. What your assignment is going to be is you've now got to come in here and do number 2, number 3, and number 4. 3 other stories that you'll graph the position versus time. Then you'll take that information. It gives you the same stories here, but now you're going to graph the velocity versus time. Once you've done all 4 stories, we did 1 together. You'll do 3 by yourself. There's one more file in here that is called, let's see, what is it? The analysis of position versus time graphs. That is what you'll fill in and turn back into me by end of today. So that will be your asynchronous activity. Right before you do that though, I'm going to share with you some more physics facts that you're going to use in solving these and other problems. So let me give you these physics facts. Slideshow here. All right, take a couple of minutes. I've got 2 slides. They're a little bit long, I'm sorry. Write as much as you can. If we start getting out of time and I advance it, take a screenshot or a picture with your camera phone. Just make sure we get these written down. I think it's important to hear them, read them, and write them. So position versus time graphs, this is something we started with last class. To determine how far, let me move this off my screen, determine how far from the detector an object is located, look at the vertical axis of the position time graph. Now here where it's saying the detector, interchange the word detector and origin. The person that originally wrote these did everything based on a lab. So it was all about approaching a detector or moving away from a detector. But just know that we can also go behind a detector because we can go behind an origin. So to determine how far from the detector an object is located or how far from the origin an object is located, look at the vertical axis of the position time graph. Second one, to determine how fast an object is moving, look at the steepness, i.e. the slope of the position time graph. To determine which way the object is moving, look at which way the position time graph is sloped. A position time graph which begins in a positive position and has a positive slope and has i.e. with the bracket there, or line, means that the object is moving away from the detector, and a position time graph which begins positive and has a negative slope means it's moving towards the detector. So write those real quick, and then I've got write those real quick, and I've got one more slide to show you. I'll give you 2 minutes on this one, and we'll do 2 minutes on the other one. Once we get those recorded, it'll be turned over to letting you work on today's work. I'll stay in the Zoom call and answer any questions all the way up until 10 after 12. So you've got lots of time to work on this stuff. All right, 2 minutes of writing, and then I'll switch it. Last class. That motion detector doesn't see me, and that one's behind a TV. I'm not actually watching a clock for the 2 minutes, so take another half minute. If you're pretty far away, take a screenshot. If you're getting pretty close, try to finish up. I'm going to advance the slide in just about half a minute. Remember, every time you see detector, you can interchange that with origin. All right, I'm going to switch to the next slide in 5, 4, 3, 2.5, 2, 1. Take any pictures necessary. Moving. There we go. Velocity time graphs. To determine how fast an object is moving, look at the vertical axis of the velocity time graph. To determine which way the object is moving, look at whether the velocity time graph is above or below the horizontal axis. An object is moving away from the origin if the velocity time graph is above the horizontal axis, positive. an object is moving toward the detector if the velocity time graph is below the horizontal axis, i.e. negative. To determine how far an object travels, determine the area between the velocity time graph and the horizontal axis, area under the curve. So this is a bit of information we were discussing earlier. On a velocity time graph, it is not possible to determine how far an object is away from the detector, and most everyday motion can be represented with straight segments on a velocity time graph. I'll let you have a couple minutes on this one, and then I want to have someone tell me about that next to last one. We'll get a small discussion going on that one. All right, I know this is so terribly exciting to sit here and write this stuff, but it's important to know a lot of these things. But let's look at the on velocity time graph. It is not possible to determine how far from the detector the object is located. So let's unmute and find somebody willing to say, why is that? Why would I not be able to determine how far from the origin I am based on a velocity versus time graph?
Because
You got it way too quick. You can get displacement from that graph, right? Don't know your initial position. You cannot determine where you are in relation to the origin. So exactly right. So very good, very nice job. If you haven't finished this, writing this, take a screenshot or a picture with your camera phone. I'm going to take it down in like 5, 4, 3, 2, 1.5, 1, going. All right, stop sharing. Okay, so that gets you the notes for the things that we're working on right now. I started the storybook problems with you for number 1 on both. I want you to do number 2, 3, and 4, and then do the analysis of position versus time graphs. Turn that into me today. We still have like 35 minutes left of class. I'm staying on the Zoom. You're welcome to bounce in and out, ask questions. I'll leave it open. So when you're working on it, if you need help, get help. But after today, make sure you're working on and completing that homework for next class. I want to make sure there's no issues with understanding and being comfortable with that knowledge. So if we do the quiz on next Monday, you're going to be ready to go.